Our next presenter is Ian Mann from the Department of Physics at the University of Alberta. Ian is an influential and world-renowned expert in space science, space weather research. His research has delivered transformative new understanding of extreme space radiation and the dynamics of near-Earth space environment. Mann's leadership at the United Nations promotes the translation of research to policy excellence, steering international efforts to mitigate extreme space weather impacts. From leading CubeSat missions to issuing auroral alerts, he tirelessly promotes lifelong learning.
So my name is Ian Mann. I'm a professor here in the Department of Physics at the University of Alberta, and my research focuses on understanding the dynamics of space weather. The dynamics driven by the sun of the outer atmosphere of our planet, how it goes from stormy weather to much quieter weather, and what the impacts of that space weather might be for ourselves here on this planet, and indeed for humans as they explore the solar system. So one of the questions that we're trying to answer is to understand how severe space weather can get and what the implications might be for us living here down on the surface of the planet, or indeed as humans go about their exploration of the solar system, going back to the moon, to Mars, and even beyond. And one of the things that we're very interested in is, of course, the physics of this process. How does it work? How does this energy that comes from an explosion on the sun, it propagates through space and arrives at our magnetized planet here at the Earth? What's the processes and what are the physical processes that transform some of that energy into the dynamics we know as space weather? And key issues that we're studying are the production of very energetic particles, so-called space radiation. These are particles, mostly protons or electrons, and they're traveling very close to the speed of light. That makes them very penetrating radiation environment for an astronaut or for a spacecraft or a satellite that might be unlucky enough to experience large numbers of these particles. We know that there's an accelerator, a natural particle accelerator operating right above our heads. That accelerator creates this harsh space radiation. Does so just like the weather. So sometimes that radiation is very calm and sometimes it's very severe. And at the times it's very severe, we know that it could be damaging for astronauts, but also, perhaps more importantly for us on the surface of the planet, damaging for the satellite infrastructure that we rely on increasingly in our everyday lives in the 21st century. One of the other consequences of extreme space weather, and we'd like to know how extreme can it get so that we can design appropriate resiliency, is effects on the power grid. So the power grid pervades every aspect of our technological lives in the 21st century, but we know that these space storms driven by explosions on the sun can drive strong electrical currents in the outer regions we call geospace, the environment where satellites fly. Those currents, just like an electrical transformer in the regular power grid, can cause unwanted electrical currents in other conducting paths nearby, and in our case that would be the electrical grid on the ground. We've seen these examples in Canada already. A very famous example is in March 1989, when there was a large magnetic storm, not a particularly large storm, but nonetheless a large storm that caused a large power outage in Quebec, knocked out some of the Hydro-Quebec power grid. Now, our question would be, how bad can those space storms get? We know historically, for example, in 1859, just over 150 years ago, that there was a very large space storm. No spacecraft at that time, of course, and no large-scale power distribution grids. But nonetheless, we know there were significant technological impacts. Telegraph lines, there are accounts of telegraph wires setting on fire as a result of induced currents being driven in those telegraph systems as a result of large currents in a large space storm. So the question, one of the questions that we're trying to ask and answer right now is, what is the physics that drives those storms? And then to translate that knowledge into understanding of what would happen today if an 1859 so-called Carrington-sized storm event happened today, and how can we make sure that we're resilient against those those damaging effects? How can we ensure that we live with the dynamics of our star, the sun, as we go about our technological existence in the 21st century? The exploration of space is also currently at a tipping point. Previously the domain of large national and international space agencies, now it's the realm of active commercial activity in space, monitoring space for the benefit of commercial interests or for knowledge of our changing planet. Space provides a unique perspective of the development of the Earth under the action of climate change and helps us understand how our changing planet is evolving. Space is also more accessible than ever before, and the new space industry is miniaturizing technology to utilize space for the benefit not just of Canadians, but of all humanity. And it's fascinating to be involved in the understanding of this space environment and to work with the next generation of students building miniaturized CubeSats and other vehicles through which we can understand space and exploit it moving forward to develop, we hope, a new diversified economy that has a footprint in space here in the province of Alberta, but also across Canada and indeed in general throughout the world.